Next talk is by Chris Drupieski. Take it away, Chris.
Thank you. This talk is the Lie superalgebra of transpositions. I'm trying to win the competition for the most elementary talk this week, so you be the judge. I was a postdoc here at UGA from 2009 to 2012, working with Dan, and I think I basically owe everything to where I am in my career now from that experience of being in the bigger algebra group. So thank you very much. And I literally wouldn't be here if not for that, because why would I have been invited if I hadn't been invited? This is joint work with Jonathan Kujawa, and as I was telling Steve, no matter how late the talk starts, it must always end on time. So when the big hand is on the 6, and it cut me off even if it's mid-sentence. But it's based on a MathOverflow question from 2022. So if you get bored during the talk, looking for something to do, feel free to go look this question up and upvote the question and the answer. So the overall sort of premise of this talk is the symmetric group is a supergroup. And what does that mean? Well, it's a group that is be decomposed into some even and odd parts. The even part of the symmetric group is the alternating group, the even permutations, and the odd part is not a subgroup, it's just a subset, but it's a set of odd permutations. And multiplication of even and odd elements preserves parity the way you expect it to. And this extends multiplicatively, extends by linearity to a Z2 grading on the group algebra. So when we use the prefix super, we mean that something is graded by the integers mod 2. So superalgebras are algebras that are graded by the integers mod 2. Supermodules are things that are graded by the integers mod 2. And we insist, whenever we're working in the super context, that the usual structure operations preserve that Z2 grading. So the even part of a superalgebra is always a subalgebra. And in this case, it's just the group algebra of the alternating group. So the question that we stumbled across on MathOverflow was from WunderNatur. Paul joked that he was WunderNatur. I don't know who WunderNatur is. Is WunderNatur here in the audience? No. I don't know who they are. I think they were a grad student at the time they posted it, but I really have no idea. So the basic question they asked was, if you consider the group algebra of the symmetric group as a superalgebra, considering the even permutations to be of even superdegree and the odd permutations to be of odd superdegree, and then you consider in turn the group algebra as a Lie superalgebra via the supercommutator, what is the structure of the group algebra as a Lie superalgebra, maybe as a product of simple Lie superalgebras or something like that? And then in particular, what is the structure of the subalgebra generated by the transpositions? And WunderNatur didn't go into a lot of detail. I don't recall what their motivation was for this question, but the non-super version of this question was answered by Ivan Marin in 2007 in a Journal of Algebra paper. So if your French is good, you could look that up. And I have a copy, but I'd have to dig it out. And at the end of the talk, maybe I'll say a little bit about what, based on our understanding of his French paper and our machine translation through Google of his paper and some other things, what we understood his motivation to be. But sometimes you might know the answer in the non-super and the ungraded case, and you might hope to bootstrap up and gain at least some information for the super case. But here you can see right away that in the super world, you're going to get a very different answer. So for super, the other part of being super, besides having a Z2 grading, is topologist sign convention. So when two things of odd superdegree move past each other, you get an extra minus sign. So the supercommutator here, if you have x and y are both of odd superdegree, the supercommutator of x and y would be xy plus yx. So just as an exercise, if I took a transposition and took the Lie bracket of a transposition with itself in the group algebra of the symmetric group, in the ordinary commutator, what would tau bracket tau be? It'd be 0. But in the super sense, what would tau bracket tau be? 2 times tau.
Oh, no,
two times the identity element of the group algebra. So in one case it's 0, in the other case it's very much not. So immediately you can see that you're going to get different behavior depending on whether you're using the sign convention or not. So the fact that maybe we didn't read through all of Marin's paper and dig through the French, well, it wasn't going to be directly applicable anyway, but we could sort of see what the philosophy was for trying to answer this. So let's start off thinking about the classical theory. So classical structure theory of semi-simple algebras, we have let's say a finite dimensional associative semi-simple algebra over the complex numbers, and V1 through Vm are a complete set of irreducibles. Then Vedderburn-Artin theorem tells us that our algebra is isomorphic to a direct product of matrix rings, the product of endomorphism algebras corresponding to those isomorphism classes of irreducibles. So it's a product of simple algebras. So in the case of the algebra, the symmetric group, everything in this talk is over the field of complex numbers. So it's a semi-simple algebra. It's a symmetric group in characteristic 0 is semi-simple by Maschke's theorem. And we know that the irreducibles of the symmetric group are parameterized by partitions, describe them just as spec modules. And so abstractly, the group algebra of the symmetric group is a product of matrix rings, just endomorphism rings of the various spec modules. And you can say how big those matrix rings are using hook length formulas or whatever for dimensions of spec modules. So as a Lie algebra, it's very simple. It's a product of copies of GLNs. And so maybe a question you could ask is there some version of this in the super world? The answer is yes. So the sort of the general theory of semi-simple superalgebras, it sounds almost exactly the same as in the classical case. And I once, on Brian Partial Day in 2016, I gave a talk, and I apparently referred to John Kujawa, John Brundon, and John Carlson, all in the same talk, but never used their last names. And John Kujawa said it was all very confusing for anybody who didn't know who I was referring to, but it's John Brundon. Some of these things, I gave this talk in San Francisco, and I was glad that he wasn't there because I was afraid that some of this would be things that he and Kleshev would toss off in an afternoon. But some of these lemmas, there's no attribution, but they're coming either from a paper of Brundon and Kleshev or the dualities and representations of Lie superalgebras book by Cheng and Wang. So a superalgebra is semi-simple if every supermodule is a direct sum of simple supermodules. So in this case, we're insisting that this direct sum decomposition be compatible with the ambient integer mod 2 grading. So it's imposing an extra restriction on that decomposition. And then the Vedderburn-Artin theorem says that if you have a semi-simple superalgebra, it's isomorphic to a product of simple superalgebras, similar to the classical case. And then another important lemma for us is if I have a finite dimensional associative superalgebra, that algebra is semi-simple as a superalgebra if and only if it's semi-simple as an ordinary ungraded algebra. So if I forget the Z2 grading and it's semi-simple, it'll still be semi-simple in the super sense. And so this tells us off the bat, group algebra, the symmetric group, will be semi-simple as a superalgebra. But then the question is, what are those simple superalgebras that show up in that Vedderburn-Artin decomposition? So what factors occur and how many times does each factor occur? Well, the simple superalgebras come in two flavors. So the first flavor is the type M simple superalgebras. So if I have a vector superspace, I can just look at all endomorphisms of that vector superspace. And this is a simple superalgebra. Simple superalgebras have no non-trivial superideals, no Z2 graded. So this is all endomorphisms. And so abstractly, it's just a matrix ring, but it has this block decomposition corresponding to the superspace decomposition of the ambient vector superspace. So like the even endomorphisms are those that preserve the superdegree. The odd endomorphisms are those that reverse superdegrees of homogeneous elements. The even endomorphisms are the matrices where the B and C blocks are both 0. The odd endomorphisms are those where the A and D blocks are both 0. And then arbitrary linear maps are sums of homogeneous parts. As an ordinary ungraded associative algebra, it's just a matrix ring of size M plus M. So this type of simple superalgebra is also simple as an ungraded algebra. And then the second flavor are the type Q simple superalgebras. And I think there was some discussion at the beginning of the month about calling these isomeric superalgebras or types. And I think Vera was part of that conversation. Maybe John, and thinking John's Brundon's abstract, he used the term isomeric, so he can explain the meaning of that term later. But in this case, if I have a vector superspace where the even and odd components are both of the same complex dimension, and then I have an odd involution. So basically this odd involution, it's an order 2 odd linear map. So just think of it as flipping, interchanging the even and the odd parts. We get this subset Q of V. So the endomorphisms that commute with this odd involution. This would be a simple superalgebra. And we can realize this. One way of realizing this is as these block matrices of the form A, B, B, A. So the things in the odd blocks are the same matrix. The things in the even blocks are the same. And as an ungraded associative algebra, this identifies just with a direct product of 2 copies of GLN, but via a non-homogeneous map. So I don't know, you can, another thing to do if you get bored, check that this is a algebra map, but non-homogeneous because it's adding together things of opposite parities. Okay, and then in the classical Wedderburn-Artin theorem, the different simple superalgebras that showed up corresponded to isomorphism classes of irreducible. So these 2 flavors of simple superalgebras correspond to 2 flavors of irreducible modules, isomorphism classes. So we say that a simple module is absolutely irreducible or of type M if it remains simple as an ungraded module. If you forget the grading, it's still irreducible. And we say that a simple supermodule is self-associate or of type Q if, when you forget the Z2 grading, it is reducible. So it's, and when I teach my classes, I always tell them it's like the Danny Ocean principle. So if you remember the trailer for Ocean's 11, Danny tells Linus, you're either in or you're out. You're either reducible or you're irreducible when you forget the grading. That trailer is not ringing any bell. It doesn't ring any bells with my students either. So the self-associate case, you can say a bit more about what do these self-associate irreducibles look like. So pi v here is my notation for the parity automorphism. So it sends even homogeneous elements to themselves, and it multiplies odd homogeneous elements by -1, and then it extends linearly. And if I have a self-associate, so a type Q simple supermodule, so this will be reducible when I forget the grading. So there's going to be some ungraded proper simple submodule, U. And the lemma says that my original irreducible supermodule can be decomposed as a direct sum of that U and its image under this parity automorphism. And that image will also be a simple module and that's not isomorphic to the thing I started with. So as an ungraded thing, this will be a direct sum of 2 non-isomorphic simples. And then using that decomposition, you can describe the even and the odd subspaces of this module. And then in terms of that decomposition, there's this formula for defining an odd involution. And so that corresponds to those type Q superspaces. Okay, I forget what the next slide is, so we'll be surprised together. All right, so sort of restating the super version of the Artin-Wedderburn theorem, I think I changed the order of the 2 names. Oops. But if I have a complete set of the simple supermodules, let's say up to homogeneous isomorphism, such that the first M of them are absolutely irreducible or of type M, and the last N minus M of them are self-associate or of type Q, then I get this decomposition of full endomorphism algebras and then these type Q algebras. Okay, so as an exercise, the dihedral group of order 2n, we could also view this as a supergroup where the even elements are the rotations, and then your favorite little reflection is odd. So you could work out the superalgebra structure of this. So that's a fun little exercise, which I'm not going to do for you, but it's in our paper on there. Okay, so let's go back to the symmetric group. So to describe that matrix ring decomposition, we need to understand simple supermodules. So keeping in mind, some of the supermodules for the symmetric group will be actual simple modules in the ungraded sense. And other simple supermodules will be a sum of two things as an ungraded object, a simple module, and then its image under a parity automorphism. So any guesses? Maybe this is not elementary if you're not well versed in representation theory of the symmetric group. This is as elementary as I think this conference could get. Any guesses? Well, you're not allowed to answer because you saw this talk in October. What?
I'm guessing again because I forgot.
What did you say? Self-conjugate partitions, those correspond to one of the two types. Things where the partition is equal to its own transpose, and then the other type would be the non-self-conjugate. And it turns out that, yeah, that's the case. That's how things break up. So let's let P of n be the set of all partitions of n, and lambda prime will be the conjugate or transpose of a given partition. And then let's look at the equivalence relation where we say that a partition is equivalent to its transpose. And just pick arbitrarily a representative from every equivalence class. So if a partition is equal to its own transpose, there's not a whole lot of choice. You just pick that partition. But otherwise, just pick one or the other for things that aren't self-conjugate. And then the simple supermodules are parameterized by this set of representatives. We call them W upper lambda. So either W upper lambda is a spec module as an ungraded thing, if we're in type M, the absolutely irreducible case, or as an ungraded thing, it's a direct sum of two spec modules labeled by a partition and the conjugate partition in the type Q or the self-associate case. Up to parity shift. So in the super world, maybe you have to decide how do you like odd isomorphisms or not. You don't like odd isomorphisms, then you have to keep track of some of these things and also their parity shifts. So the type Q supermodules, in this case, you can view that odd involution as an even isomorphism between that module and its parity shift. So the type Q things are even isomorphic to their parity shifts, whereas the type M supermodules are not even isomorphic. There's an odd isomorphism, but not an even isomorphism between the module and its parity shift. And this has to do with the fact that over the alternating group, this spec module decomposes into two non-isomorphic things. And these have to be the homogeneous subspaces. So it's not even isomorphic to itself. Okay, so, and before I get to the results, you also have a nice multiplicity-free restriction theorem, just like you do in the classical case. So you can describe the restriction of one of these W lambdas to the next smaller symmetric group in terms of the usual Young lattice ordering, where one partition is directly below another if you get it by removing a single removable box. And this is, I guess, literally a multiplicity-free decomposition if you only allow even isomorphisms between modules. Otherwise, I guess you could say, you allow odd isomorphisms, then W mu and pi of W mu, the parity shift, are isomorphic. So it depends on how picky you want to be about what it means to be isomorphic. Okay, so from this sort of classification of the modules, we get our description of the group algebra and the symmetric group into these type Q factors and these type M factors. And I think I have all my indices correct this time. And then as a Lie algebra, it's direct sum of the corresponding Lie algebras, type Q algebras and general linear Lie superalgebras. Okay, so now let's let D of G be the derived superalgebra, derived subalgebra of a Lie superalgebra. So the derived algebra of general linear is a special linear. And in this case, it's these block supermatrices where the super trace is 0. So the trace of A minus the trace of D is 0. And in the type Q case, this SQ notation is from one of Vera's papers. The derived subalgebra are these block matrices where the odd block has trace 0. And so the main theorem that John and I calculated is if we let G sub n be the subalgebra generated by all transpositions inside the group algebra, the symmetric group. And then we let T sub n be the sum of all the transpositions. So that's an odd element, an odd homogeneous element. It turns out that the subalgebra generated by the transpositions is the full derived algebra of the original group ring, direct sum with this space spanned by that operator T. So it's a sum of copies of these SQs and these SLs plus this extra odd operator. And one direction of this inclusion, this equality is relatively easy to see because you can just check the by looking at the image of certain things inside these SQs and SLs, that a certain set lives inside the derived subalgebra. So one direction is easy. The other hard part's the other direction, showing that the full derived algebra is inside this Lie algebra. Okay, so what are some of the ideas behind the proof? Big hand is getting close to 6. So it's sort of broken up into 4 parts. And this strategy, it very much rhymes with Marin's strategy from the classical case. So for us, the hard part, first step that we did is to try to show by induction. So using that multiplicity-free restriction theorem, trying to look at the image of our Lie algebra inside one of these endomorphism rings. So projecting onto one of these endomorphism algebras and seeing how much do we get. And by induction and by some brutish force, we can show that we calculated that you get everything that you think you should get. If the original theorem, if the theorem at the top is true, then this is what you should get when you project down. And it's using the inductive description of the restrictions and some eigenvector bases coming from simultaneous action of Jüstensberg elements. And then sort of retroactively, we can deduce that the even part of our Lie algebra is reductive, and hence the derived subalgebra of the even part is semi-simple. Because after we compute the image of all these, the image of our G inside each of these endomorphism rings, we can see that these W lambdas are all semi-simple over that image. And so the direct sum of these modules becomes a faithful finite dimensional, completely reducible module, and then hence G0 is reductive. Marin is able to do reductivity first, but we have to sort of we have to understand both even and odd stuff. So I don't know, maybe there's some other way of getting directly to reductivity, but we had to do this kind of ugly calculation first. And then the next step is to try to show that your derived subalgebra of G0, that this semi-simple thing is as big as it should be if your theorem is true. So by semi-simplicity, it's a product of simple subalgebras, of special linear algebras, and you just need to show that you have the correct number of those factors, that you have as many as you think you should. And some of the key ingredients are things like for these W lambdas and W mu's don't have any simple constituents in common over the alternating group unless lambda and mu are equal. And then for n greater or equal to 5, this derived algebra can distinguish irreducibles for the alternating group. And this is sort of coming from the fact that this derived algebra contains all of these products of 2 transpositions. So you can think about what super bracket would I take between transpositions or things generated by transpositions to get these elements if I, J, K, and L are all distinct. And these things for n greater than or equal to 5 generate the alternating group as an associative algebra. But once you show that this derived algebra of G0 is as big as it should be, then it's just a hop, skip, and a jump to get everything you wanted. You show that the odd part of derived of the group algebra is inside your Lie algebra, and that essentially generates everything. So, I mean, this does rhyme with Marin's argument, but a lot of the details are different. So here again is the end result. And when I think at one point, when I first posted this on the archives, I was following my hero, Dave Benson, and posted a link to the article on Facebook. And Dave asked, what was the dimension? So here's the dimension of this algebra. So basically, you lose 1 dimension for each of these equivalence classes of partitions. But then you get +1 back for that extra odd operator. Okay, so I said I would say a little bit about Marin, like where this was coming from in the classical case. So to our best of our understanding, Marin's motivation was he was looking at models over Hecke algebras and tensoring two of those modules together. And that's no longer a module over the original Hecke algebra, but it is a module over the braid group. And he wanted to understand how does that tensor product decompose. And through his thesis and some other papers he wrote, he evidently proved that the decomposition of that tensor product was controlled in some way by this Lie algebra, the Lie algebra of transpositions. So that's why he was interested in calculating it. And he's able to figure out right off the bat that the Lie algebra of transpositions is reductive, has a one-dimensional center. He's able to get this very quickly from general principles. And then he uses a lot more Lie theory to figure out the actual description. And his algebra is less than half as big as ours. Ours is we got quite a big thing, almost this full derived algebra. Well, the full derived algebra plus one extra dimension. So we got pretty close to the entire thing. But his is a lot smaller. So his notation is a little different than ours. His E's and F's don't include any hook partitions. So these all get set to the side. So here he is looking at so his E mod tilde. He's taking sort of equivalence classes of non-conjugate, non-self-conjugate partitions. And for each one of those equivalence classes, he gets a single SL. Whereas in our case, we were getting a type Q algebra. And the type Q algebra has, we had a derived part of that. And that had an SL in the odd block and a GL in the even block. So we're getting something that's twice as big as what he has. And then over here for the type F parts, we were getting a full matrix algebra. He's getting either an orthogonal or a symplectic Lie algebra. And don't ask me how exactly it turns into orthogonal or symplectic, because that's part of the French paper that I didn't read. But OSP here is, I guess, French notation meaning either orthogonal or symplectic. It does not mean the Lie superalgebra OSP. And then the last thing, the first factor that he's got, all the different hook partitions that show up in the classical case all get sort of lumped into one factor, because among the hook partitions, you've got one partition that has n-1 parts and then single one in the next row. And I think that corresponds to an n-1 dimensional representation. Okay, I'm glad I got that right and didn't embarrass myself. But that n-1 dimensional representation, that's giving him an SL n-1. And then there's no other factors corresponding to any of the other hook partitions, because that information is redundant in some way. Those other irreducibles are exterior powers of that n-1 dimensional thing. So he's able to throw most of that other information away to get this description. So he ends up with something that's, on the order of, well, it's less than half the size of our Lie superalgebra. So we get something that's a lot bigger. And then, so here's a picture from 2010. When I was a postdoc, there was a 2-week-long workshop and summer school. So here's some baby pictures of BNP. I don't know which of the many BNP papers you were working on back then. What are you up to like now? BNP 12? S. The audience wants fourth cohomology of finite groups of Lie type. Give them what they want. You've given them first, second, third. The audience demands fourth cohomology. And then here was another paper. Here was another, maybe this is from later in the week when they did a panel discussion. And these are some of the good pictures. I think everybody in these pictures is here in the audience. Thank you.
I already asked this since they said I forgot to ask me about this. Is there any interesting branching, maybe in your case, or yours is pretty big, maybe in the original Marin case, your shift down from the whole, we output the one generated the symmetric positions. And then maybe like in Tableau.
I don't know. I'm not trying to understand what you're thinking.
You described this. You have irreducible models for this Lie superalgebra, the whole thing, and then you also have a smaller one inside. There's still irreducible pairs, so there's no branching at all. All right. Is there branching in merit?
I mean, as long, if your sub-algebra,
Because it contains all. So.
I would draw.
I mean, maybe one thing I should say is, we looked at the sub-algebra and the super gets generated by all transpositions, and based on some small n values calculations, if you only start with the adjacent transpositions, you get something smaller, and I don't know what that is, but it was convenient to include all the transpositions. In Marin's case, if he starts with just adjacent transpositions, then some fluke of commutator identities, he gets all of them for free. So that's a question of something to be calculated. Another question that Dave asked before, and maybe doesn't remember that he asked, was what about types B, C, and D? The abstract said time permitting. It didn't mean time permitting in the talk. It meant time permitting before the talk over the last several months.
No, I asked about characteristic P, you just got my.
Characteristic P, I don't know about that. But I mean, John and we have looked at types B/C and D enough to see that at least some of the main steps in this argument, there's enough sort of structure known in those cases that it's plausible that there should be a theorem you could write down, but we haven't. And also, the computer calculations are harder. This was by induction. The case n equals 4 or 5 was in gap because I don't know how to do it in Sage. So somebody's better at Sage. Maybe they can figure out how to calculate this to get it.
Other questions? Well, let's thank Chris again for